Okay, good. Right, so what I'm going to talk about now is a session which I'm still struggling a little bit in terms of trying to come up with the right name for this. So I've called it Bringing the Performance of Structs to Java, sort of. And we'll see why that is as we go through. And this presentation is all about a project that was started by the CTO at the company that I now work for, Azure Systems. And it's called the Object Layout Project. The goal of this project is to try and match the speed that you get in languages like C and C++ from some commonly used memory layout schemes. And what we want to do with this is to enable you to get a better performance for your application using these things without having to change your code. Well, maybe a little bit, but not really substantially. Using a new collection, that would be all you'd have to do. But there's no radical changes to how you actually create your code. And the key thing here is it says in red, it's about speed for regular Java objects on the heap. And those are the three things which I'm going to come back to. And I'm going to say that several times during the presentation. Speed for regular Java objects on the heap. Now, the project is actually not looking at some things. So there are three things it's not looking at. One is it's not trying to improve the footprint of your application. So this project will not reduce the amount of memory that your project requires. It won't necessarily increase it, but it won't reduce it. It's not looking at off-heap solutions. So we're not trying to do this using native memory, not trying to bypass the heap and bypass the garbage collector in any way. And the other thing it's not doing is looking at the idea of immutability for objects. So the things that you can use with object layout are still regular Java objects that you can change in terms of their state if you want to. If you look at some of the other projects which are being developed and being proposed in the Java space at the moment, you might think that some of them there is some overlap in terms of the goals for those things. So if you look at value types have been proposed as a new feature, well, are being proposed as a new feature in JDK 10. And value types are all about having immutable objects, which are like objects. Well, sorry, they're yes, immutable. They're like objects, but they're not objects. So it's if you wanted to treat something like an int as if it were an object, then a value type is something that you would use for that. So you could potentially have a collection, a list of ints rather than integers. In terms of the relationship between value types and object layout, there's no overlap in terms of the goals. Packed objects is another project that people are working on at the moment. And this is more about how you can work with objects which are outside of the heap. Things like native code, where you want to integrate native code. It's looking at ways that you can have a replacement for JNI, foreign function interface. Again, in terms of the goals of that project and the goals of the object layout project, no overlap. Object layout is focused on a different problem. There is some overlap in terms of what they do. The goals are completely different, but in terms of what they actually do, there is a little bit of overlap. But you can think of that in the same way, as it says here, that you have two types of collections. So you've got an array list, you've got a hash map. They're both collections, but they do things in very different ways. So that's the kind of overlap that we're talking about here. If we look at a nice Venn diagram of these three projects, you've got object layout, you've got value types, packed objects. The qualities, properties of value types is that they are immutable. They are values, so they don't change. You reference a value, it has a value, it doesn't change. You can use them for return values. classic use of value types is to be able to return multiple values from one method without having to encapsulate it in an object. So you can return a tuple rather than a single value. These are either on the stack because you're using them to return values from a method, or they can be on the heap. So you can use them anywhere that you can use values in Java. This requires new code. If you look at the way that value types, certainly the proposals that have been made so far, are going to work, then you will have to write new code. You'll have to modify things, write things in a different way. Packed objects. These, as I mentioned, are very much off the heap. So it's when you're dealing with native code, native interfaces, foreign function interfaces, where you might have data which is not on the heap. How do you use those? It's about sharing data between Java code and native code. It's about having very precise layout control. Typical example of that would be if you've got some native code that is reading packets from TCP. TCP has a very well-defined layout. So the data that you're processing is going to have that well-defined layout. You need to keep that well-defined layout, and that's what a packed object is going to be addressing. Again, that will require new code. There will be a different way of doing things to the traditional way of using JNI. There will be a different way of accessing these objects. If we look at object layout, the three things that I've already said. Speed for regular Java objects on the heap. So it's really quite simple what we're trying to do with this. And it is that these objects will be usable by all existing code. So even though we provide a different type of collection, the code that you'll write will still be exactly the same. You won't have to change the way you use generics. You won't have to change the way that you use JNI. None of that will change. And there is a little bit of overlap between those three projects in terms of where you might want to use these things. And so there is a situation where you might have an array of small footprint values that you need to process. And so you could potentially use all three of these things together. In terms of the origin of the object layout project, it all came about from a discussion that was had about the fact that people needed structs in Java. Now, so everybody here done C or C++ programming? Okay. Right, there's a couple of people who haven't. So structs are really like an object in C. They're a way of grouping together values, data, in a single unit. So in Java, obviously, we have objects. We can create them. We can manipulate them, whatever. In C, you can create a struct, which has maybe some ints, maybe has some chars, whatever. But it's a way of grouping together that data. Now, what you find is that structs are very good because they keep data together in a particular format. And as we'll see, that gives you some real benefits in terms of performance. Wouldn't it be nice if we could do the same thing in Java? And people have tried in the past to replicate that. They've been looking for ways of getting this better performance in terms of the layout of the data that they're using. They can do things like using sun.misc.unsafe, the private API that's available in the JDK, which allows you to dig down into the memory and actually manipulate things at a very low level. But that's really not a good idea, especially with JDK 9 deprecating sun.misc.unsafe and JDK 10 changing the way that works. So it's not really a good idea to use a private API for that. C and C++, get it for free because they have structs, so you can just use them, make them work, great. So then people said, well, okay, well, that's good. Okay, so we need structs, but we already have structs in a way. A struct is just a way of grouping together data in a particular format. You define the format, great. What we have in Java is called an object. You can define what data you want to go in that object. You can have ints, you can have chars, you can have strings, whatever. So what's the big difference? Well, it's all about saying, how do we capture the way that structs work in Java in such a way that you can improve the performance of objects without having to change your code. And that's the really key thing, is how to figure out a way of doing this without having to change your code. So let's look at where speed comes from in terms of C. So I'll say C, but it's not really C and C++, but C. So there are two things that the struct allows the compiler to do, and therefore your code to be able to take advantage of. One is what's called dead reckoning, the ability to figure out where something is in your data. And the other is streaming of arrays of structs, so the ability to iterate over a collection of data. Let's look at that in a bit more detail. So here's a struct in C. So as I said, a struct is just like an object if you in Java. So you say, got a struct called square, and it's going to have an X and a Y position for one of the corners, and it's going to have a size. So I've got 3 ints. And then I can create a struct simply by saying struct square S. Wonderful. That puts it on the stack. And if I look at what's on the stack, what I'm going to find is I've got my struct called square, and it's got 3 ints. So literally on the stack are 3 integer objects, one after the other. Okay. In terms of dead reckoning, let's say I create an array of structs. So in C, I'm actually going to have to allocate the memory explicitly. I don't have the idea of a new operator, so I need to allocate some memory using malloc and create a pointer to that, which I can then use to reference an array and index into it. Here I'm creating an array of 5 elements, and if I look at them in memory, they'll all be contiguous. If I want to figure out where one of the pieces of data are in that array, let's say I'm looking for the 4th element of the array of structures, and I want to get the Y value of that. How can I do that? Well, it's actually very simple. Using dead reckoning, what I can do is I can say, okay, I know where the data starts. So this is the address of my area of memory that I've allocated. So that's my starting point. I know that I'm indexing to the element number 3, which is actually element number 4, because bizarrely in computer science we start counting from 0. So we have to move to the 4th element in the array, which is number 3. And then we add the size of an int to move past the x int to the y int. And that way we can find y very simply by doing a mathematical calculation. That's very fast, because of course we can convert that into machine code, and we can very quickly identify where that particular element is. If we look at streaming of arrays in C, so we'll take our same array of square structs, which are contiguous in memory. They have what's called a stride, which is the size of the struct. If I want to iterate over that array of squares, it's very simple. I start off with my pointer at the beginning of that area. I increment it by the size of the struct. When I go to the next one, I increment that by the size, I do 2 times the size of the struct plus the base address. Third one, 3 times the size of the struct plus the base address, and 4 times the size of the struct plus the base address. This is very good because in a situation like this, the hardware and the virtual machine, or not the virtual machine, the hardware and the compiler can take advantage of things like prefetching. They can take advantage of things like cache lines, so that these can happen very, very quickly. You know, the compiler will spot that these things are being accessed, and the code can then, and the underlying processor can then say, right, let's prefetch the next one so it's ready when we get to it. And that way we improve performance quite a lot. Let's look at the same approach if we use Java. So here we've got a class called square. Same idea that we had with our struct. It's got 3 ints in it, looks very similar, just calling it a class rather than a struct. Int x, int y, int size. And if we want to create a square, we do what we always do, we say square equals new square. call the new operator, calls the constructor, constructs an object. And if I look at what's stored in memory, it looks very similar. I've got my square object, I've got 3 ints, wonderful. However, things get a bit more complicated. If I have an array of squares in Java, this is what I'm looking at. I create an array of squares, new square, 5. Now, if I'm lucky, when this array is allocated and I allocate the squares for that, I might, just might, get them contiguous in memory. So at that point, it still looks very similar to the way that we had things in C. But once the garbage collector runs, because these will be allocated in the young generation, once the garbage collector runs, and after a while they'll be promoted to the old generation, we're potentially going to get something like this. Objects get moved around in the heap because of the way the garbage collector works. Now, some people have said, well, you might actually still get them contiguous in memory once you've done the garbage collection, because if you've got a copying collector, they might actually end up contiguous in memory. Quite true, they might. But the point is, there's no guarantee that they will. So, yeah, they may end up contiguous, but they may just as easily end up spread around the heap. So we can't rely on the fact that all these objects are going to be contiguous in memory. So that idea of striding, where we're going to iterate over the array of structs, doesn't work. The VM, the hardware, won't be able to do prefetching because it won't know where the next object is going to be. In order to find the object, we have to go through the object reference. So we've got a level of indirection, we've got to follow that reference to find the object. Things get more complicated though, because we have inheritance. And so if I have an array of square objects, I can quite happily place a subtype of square in that array, because it's still a square by virtue of the fact that its superclass is square. So let's say I've got a filled square that's got some more information and it's bigger. So now I've got a bigger object there, and again, even if they were contiguous in memory, which at that point they couldn't physically be because of the fact that we've changed a reference, you'd have to account for the fact that that object might be of a different size. So looking at the semantics of how structs work versus how objects work, in C, what you've got is an immutable array of exact same size structures. Once you've created an array of structs in C, you can't change it. You can't make it bigger, you can't make it smaller. It is what it is. And the things that are stored in there are the structs that you've defined in that array. So you can't change those in terms of their underlying structure. You can change the values in them, but you can't change what they contain. Can't change their size, can't change how many there are. In Java, when we deal with an array, what we have is a mutable array of same base type objects. We can change the references to the objects in that array very easily to other squares. We can change the array references to objects of a subtype, so we don't have to have the same one, as we saw in the diagram. We can change the object reference to in our array. So, okay. All of this means that we can't depend on the structure that we had in terms of our memory layout to enable us to do dead reckoning, can't enable us to do the striding and therefore prefetching that we had before. So what object layout is trying to do is to enable us to find a way of having this struct-like quality of things and be able to create arrays of them and do dead reckoning and do striding and prefetching without having to change any of our code. So what we're looking for is a way of replicating primarily a struct array of some type, like foo. And we're also looking at two other examples of how structs are used in C. So we might have a situation where you've got a struct which contains a struct within it. And you might also have a struct where you've got a variable length and then an array of something at the end. So it could be an array of chars, for example. So all of those you can easily create in Java. There's nothing here that's weirdly different. You can do all of this in Java using classes, using objects, using arrays. Okay. But what you can't do is match the speed of C, because we don't have this ability to understand exactly what the layout is, so we can't use the techniques that are used by C in terms of its native code. In terms of this project, what we did was we modeled it on how java.util.concurrent started. And if you go back in history to JDK 5, in fact before JDK 5, the problem was that Java didn't really have any good ways of handling concurrency. Literally, you had the thread class, and there were 4 primitive operations: sleep, wait, notify, and interrupt, that you could use to try and synchronize code that was using multiple threads. You had synchronized blocks, you had synchronized methods, but it was very low level. So java.util.concurrent started life as a project by Doug Lee. He was a professor at a university who set about defining a set of APIs that would make life a lot easier for Java developers writing concurrent code. So he created it as a separate project, didn't try to extend Java, he just wrote it as his own set of libraries, made it work, and used all of the standard Java class APIs to do this. So it didn't require any changes to the JVM. It was just a new library. However, that meant that to start off with, it was very easy. You could just add the class library to or the Java file to your class path, and you could use it in your code. But it didn't give you any advantage in terms of speed. But so in terms of like the atomic long operation, for example, you can do that with a synchronized block. But once that had been kind of integrated into the libraries, so that was absorbed into JDK 5, it meant that the JVM underneath could now look at what was happening in terms of the code and optimize it. So this is what's called intrinsifying the code. So it looks at something like an atomic long compare and set, and rather than doing it using synchronized blocks, synchronized methods, it actually uses the underlying x86 instruction set and does it as a single operation, much, much faster. So it's a way of starting off producing a set of code that works using just standard Java, no JVM changes, and then as it's absorbed into the standard class libraries, it can be optimized by the JVM because it knows what it's doing. So from the point of view of the object layout project, the way we started was to, as I say, look at how could we replicate this idea of structs in terms of memory layout, but without changing any of the language. So we needed to look at how we could just use Java classes, and we started off targeting Java SE 7. There's a specific reason for that, rather than earlier versions, which we'll see in a moment. But starting off with Java SE 7, because there was a particular API we wanted, and then making it just a standard set of class libraries. Once we'd done that, we could have the JVM and the JDK recognize that it was using this bit of code, and then do some intrinsification and improve the efficiency of it by recognizing it and going, oh, okay, we don't need to do it using pure Java code. We can actually dig down into the lower level code, JVM. We can use something like unsafe. We could use machine instructions, do whatever it is to improve the speed of that. Let's start then by looking at how we can deal with an array of structs. And to do that, we have a new class, a structured array. And this is a generic type, so it has a type parameter associated with it, T. And what this is a collection of object instances of an arbitrary type, but an exact type. That means that you can't have subclasses. It has to be all the same type of object. No subclasses of subclasses or anything. It's exact same type. So that captures exactly what happens with an array of structs in C. because remember, you have to have the same struct in your array. It is, funnily enough, arranged like an array. So it is a sequence of objects which are accessible by using an index into that array. So you can get, based on an index, and return the object that is at that position in the array. The collection is immutable. So we have exact same type elements within the array, and you cannot change them. So you have to leave the same objects where they are. You can change what's inside those objects in the same way that you can with an array of structs, but you can't change the reference that would be used. So it's not like we had in our previous example where we could change one of the squares, or we could change it to a filled square. You can't change the objects in the array. So there's a get method, because we can retrieve the reference to the object, but there's no put method, because you can't change the reference to the object. Oh. Yes, so you can put like a square object in there, and you can change it. So if you want to change the x and the y and the size, perfectly valid. So the thing that's in there can be changed, but the reference to that object cannot be changed. So you have to leave that object there. Now, in order to create these, we instantiate them via a factory method. So we use StructuredArray.newInstance, and then we tell it the type of the class that we want to store in our structured array. So we give it some class.class. So it knows the type of the object that's going into the structured array, and we tell it how big the array is going to be. So in this case, 100 elements. All of the elements are constructed at instantiation time. So when you create your structured array, 100 elements of some class will be created and placed into the structured array. Now, quite often, you don't just want to create an object by calling the default constructor. You may well have a situation where you want to pass some parameters to the constructor when you create the object. So that is supported. You can define ways of constructing your objects based on the index into the array. And that way you can pass different parameters to the constructor. There's a specific class called ctor and args, which is short for constructor and args, that you can use to define how the object is going to be created when it's placed into the structured array. And in fact, let's have a look at how we do that. So here I've got a very simple class called foo, and it has a variable called index, and the constructor takes a parameter called index and then just sets it. So we want to set the index when we create the object. If we want to do that using our structured array, what we would do is something like this. So we start off by retrieving the constructor associated with the class foo. And we retrieve the appropriate constructor, which is the one that takes a parameter of type long. So this is going to tell us, or give us a reference to how we can call the constructor within our code. Then we create a structured array of type foo, and we say, give us a new instance of that. We pass in the class, foo.class, so it knows what type to create. We pass in this context, which I'll come back to, and then we pass in the size, which is 8. So we're going to have 8 elements. The second argument is a lambda expression. So the lambda expression is a way of describing how to construct the objects. So it gives us complete freedom in terms of defining how we want to construct the object. So here we provide a constructor, and in this case we're getting a context from the new instance, which will enable us to find out what the index of the array element is. So we've got our context, and then we call new constructor and args of type foo, because we want to create a new foo object. We pass in the reference to the constructor so that we know what object we're going to be constructing and how to construct it. The context .index gives us the index number. So when we create 8 objects for this. Each one will have the index passed as a parameter to its constructor when it's constructed. So you'll end up with 8 objects from 0 to 8 with stored values. So that solves that problem very nicely. Liveness. Question at the back. Can we get a wood? The previous slide. Yeah, so context.getIndex is the parameter that's being passed to the constructor. So that will return a long, and we can then pass that to the... So this is a fairly simple example. Because that comes from the context. Remember, this is a lambda expression. So the lambda expression is used by the new instance method, and context will be populated with the index as the objects are created, and that will be incremented. Yep? Okay. So, structured array liveness. Originally, when the designers of this were thinking about this, they thought, well, if there is a reference to an element in the structured array, then we should keep the structured array alive. Because that's what happens in other runtimes. Because if you look at C, you allocate memory for an array of structs. If you've got one of them alive, you've still got that piece of memory alive, and so you keep the whole thing alive. Okay. But in terms of Java, objects have real liveness. It's already tracked by the JVM. So the JVM knows what objects are referenceable, what objects are no longer referenced, and that's how the garbage collector works. And if you think about it, it actually, a structured array is just like a regular collection. It's like a list, it's like an array list, has the same kind of properties. And certainly if you've got an array list, and you've got references to objects in that array list, then if you no longer have a reference to the array list itself, that can be garbage collected. But the objects which you still have references to from other places don't need to be garbage collected. So it makes very much makes sense to say that in the case of a structured array, if we have a reference to the structured array, we keep it alive. But if we remove that reference, then the structured array can be garbage collected. And any objects which don't have any other references from outside of the structured array can also be garbage collected. The kind of argument there is that you could say, well, if I had a structured array that had 1 million elements in it, and I had a reference to one object that was still being used, you don't want to keep a reference to all of 1,000,000 or 999,999 objects which aren't being used anymore. So you might as well garbage collect all of those. So in terms of liveness, it works exactly the same way as it does with normal Java. That's the takeaway from that. It's just the same as in normal Java. So in terms of the benefit of that, there's nothing special that has to be done in terms of the structured array. It is treated just like any other object. It's treated just like any other collection. So the garbage collector can identify when it can be collected and when objects that it has within it can also be collected. So that's great. Elements of the structured array are just regular objects. So that means that they can be used anywhere else. You can pass a reference from an object that's stored in the structured array to other parts of your application. You can use it in other collections, you can use it in other parts of your code, absolutely no problem. Because it's just a regular Java object, you can apply locking. You can use it as a lock, you can use the monitor on it, no problem at all with doing that. You can use the hash code as an identity for that object. Again, it is just a normal Java object, so no issues with that. And you can use it in exactly the same way as any other Java object, even though it's being stored in a structured array. So this is very natural, very easy to support in terms of the JVM. Now, in terms of the structured array features, first is that indexes are longs. This is, after all, 2016, so we need to deal with potentially big collections of data. Nested arrays are supported. So you can have a structured array which has elements within it which are themselves structured arrays. You can create multi-dimensional structured arrays, you can compose them, as we'll see in a little bit, and essentially put whatever structure you want to your structured arrays. Build it up in whatever makes sense for your application. Structured array is subclassable. So if you want to, you can add some extra functionality around that in order to make your structured array do whatever it is you want. So it's kind of like saying, okay, you've got a list and you want to have an array list. In this case, you can have a structured array, and then you can have a my structured array that does something a little bit different in terms of adding functionality around that. Structured array is not constructible. So we use factory methods in order to create structured arrays. And that allows us to do things like using the constructor and args to define how the constructor is going to be called when the objects are created. So we have to use factory methods in order to construct them. So anybody spot the catch-22 situation there? Problem is, how can you have something that is subclassable and yet not constructible? Because by definition in Java, in order to be subclassable, you have to have a publicly exposed constructor in the superclass. So it's subclassable, but it's not constructible, which is a bit of a conundrum there. Okay, how do we deal with that? Well, the answer to that is what's called constructor magic. It's a nice idea. It's actually quite simple. What it does is it uses a context for the structured array, so that if it has a publicly accessible constructor, because it has to in order to be subclassable. So it has a publicly accessible constructor. When that publicly accessible constructor is called, it will check to see where the call is coming from. If the call is coming from the factory method, it will say, okay, that can be used, construct an object, return it. If the constructor is called not from the factory method, so if somebody is trying to do it, or from the subclass, I should say, if somebody's trying to do something outside of that and try and call the constructor, which they shouldn't do, then it throws an exception. So it basically checks where the call to the constructor comes from, decides whether it's valid. If it is, it returns. Otherwise, it throws an exception and won't allow you to call the constructor. In terms of the implementation for the JDK, what we did to optimize things is introduce the concept of contained and container objects. This is not really radically different, but it makes it easier in terms of improving the efficiency. So container objects are just regular objects. Nothing different about them, except that the JDK understands which type they are. If you've got a contained object, then the JVM has to have, or has a way of figuring out what is the container that holds that object. That's the important thing that the JDK needs to understand, is that if we've got, in a case of our structured array, a number of objects, if we find an object and it says this is a contained object because it's in that structured array, then the JVM has a way of identifying which structured array is the one that contains that object. So it's like a back reference to the container. If the garbage collector comes along and says, right, I'm going to move this object, it checks to see if it's a contained object. If it's a contained object, then it has to go, right, I'll go back up to the container object, figure out that there's actually several objects that make up this contained object, and move them all at the same time. That way, we maintain the locality of reference. So all of the objects are moved as a single thing. So even though the garbage collector looks at individual objects, what it's going to do is it's going to test to see whether that object is part of a structured array, and if it is, it will move all the objects that are in that structured array as one unit to keep the contiguous memory. That's very simple to implement in all of the way that the JDK garbage collection works. So in terms of Azul's product, we've looked at Zing, our JVM, and our garbage collector, and we figured that's actually very simple, and we figure that even hotspot is very simple to do as well. Once we've done that, we can then optimize things. So we now know that we can move things as a single block. We know that we can maintain that contiguous area of memory. We know that things are not going to change in terms of size, not going to move around. So in terms of streaming, we immediately get the benefits that we saw before, because now we don't have to follow an object reference in order to find the elements. We can simply go, right, look at the next one, look at the next one, because it's contiguous in memory. Take advantage of prefetching, take advantage of caching. In terms of the dead reckoning that we saw before, then it's a little bit more complicated because the compiler needs to do some extra work as well. Unlike with Structs, where you do have just the data, in the case of the objects, there's other stuff. There's object header, there's various other bits and pieces that sit around the object. So it's not as simple as just saying, well, if I want to find the y value in my square, I simply go to the address of the square object and increment by 1 int, because that's not going to get you past the object header, it's not going to get you past other bits of the object layout. The compiler can work all of that out. As I say, there's a bit of work to do in terms of the element size and body size. But there's already optimizations that have been used quite extensively that we can take advantage of. So if you look at things like class hierarchy analysis, if you look at things like inline caching, the way those things work, it's a similar type of approach, so we can use that work again. If we look at how the other parts of the things we're trying to replicate work, so either a struct in a struct, and a struct with an array at the end. So again, if we look at an encapsulated struct in C, what we've got here is a line struct, which contains endpoint 1 and endpoint 2, which are themselves struct, which have int x and y. And again, layout in memory is just sequential, contiguous in memory. If we look at that in Java, we have the issue of the fact that we use object references. We don't have addresses, they're implicit pointers to objects rather than the objects themselves. So in terms of my line object here, I've got two things, endpoint 1 and endpoint 2, which are both references to objects. So in order to find the point, I have to follow the reference to the actual object. If I want to make that work with the new object layout code, I need to do something like this. So I can define my class line, and I can say that this is going to have within it endpoint 1. And so I make that a final point. But now I need to tell the compiler that this is going to be intrinsic to this object. To do that, I first need to get a reference to a method handle. This is why we need Java SE 7, because we need a reference to a method handle, so that we can then use the method handle to say, okay, create this as an intrinsic object and construct it within this object. And that's really just telling the compiler and telling the JVM underneath that this object is going to be part of the surrounding object. So we say, okay, construct it within using the lookup that we've got for the method handle. We're going to create endpoint 1, and we're going to reference back to this, which is the surrounding class. So what then happens is that the JVM can make the struct, as it were, so object, intrinsic to the enclosing object. So rather than having it as a reference to somewhere that might be anywhere in the heap, we know where it's going to be. It doesn't change the fundamental way that this works. So we're not changing the idea of having a pointer. We still have the reference to the object. It's just that we know where the object is. Bear with me for a second. And so one thing we do have to deal with is dealing with reflection, and if people do reflection-based overrides, but that's a little bit more complex. So essentially what we end up with now is treating this as a single piece of data. So we have our line object, which still has the 2 pointers, but now we put the points contiguous after that and treat it as if it was one thing. So this is now the same contained container object. The 2 points are referenced, but if we want to, we can move that all as a single thing. Garbage collector will understand that, and we can then say, okay, if I want to reference the point, rather than having to take the address of the object and following it, I know that point 1 is actually straight after this object, so I know where to find it. So you can do dead reckoning to get to the struct or the point, rather than having to follow the object reference. Struct with an array at the end. This is essentially a subclassable array. Semantics are well captured in terms of subclassable arrays already. What we do here is we basically create a specific type based on each primitive. So there's a primitive long array, a primitive double array, and so on. And there's also a reference array, so if you want objects rather than primitive types, you can do that. Structured array is also subclassable. So what we can do there is we can essentially capture the semantics of the array of structs at the end of our struct. So we can use a structured array as a way of putting our array at the end of a struct. The other thing is that all of these are composable. We can put them all together. So what we can do is we can start off with our heap. So this is where we're going to put everything. We can then say, okay, let's create a structured array which contains structured arrays of type foo. So this gives us our 2 levels of structured array. Within that, we have obviously objects which are structured array of type foo. That will contain objects of type foo. Each of those will contain objects of type foo. And then those could then have structs or objects intrinsic within those. So we could put bar and we could baz as objects within that. And all of that will be laid out in memory. And then we'd also have like a variable length array at the end, or a fixed length array at the end, so that we've got all of these things together. All of that will be one big flat array of data in memory. And so you'll be able to do striding, you'll be able to do dead reckoning to figure out where individual pieces of data are without having to go through a lot of pointer manipulation and pointer following in order to find the data. So it shows that you can basically decide what you want in terms of the structure of your data. You can make it as complicated as you like, and this will work. Status-wise, there is code on GitHub for this. You can check it out. There's ObjectLayout.org. It's pretty mature in terms of the project. Gil Tinney, who's the CTO of Zool, he likes to say that he's still working on the spelling. So he's still working on what the naming of some of this is. We've done intrinsified implementation for Zing. We're looking at doing one for OpenJDK. We have about a 6% performance improvement using hashmap.get if we use a structured array. So, I mean, you might think, well, 6%, that's not great. But, if you're using hashmap a lot, that could be quite significant in terms of improving performance. Obviously, the next step for us is to put this forward as a project that can be included into the JDK. There'll be some sort of JEP that will need to be filed, a Java JDK enhancement proposal. Maybe we'll get to add object layout to Java SE 10. We're too late for Java SE 9 now, but maybe Java SE 10. And just to summarize, basically, as I say, new classes in object layout. Idea is that this will work out of the box on Java SE 7, 8, 9. Don't need any syntax changes. It's just using a new collection, no new bytecodes, no new JVM behavior. What we can then do is have the JVM change underneath transparently to developers and just say, okay, they're using structured array. We now understand how that works at the JVM level. We can improve the performance. We can make it go faster. And with 32 seconds left, I have Q&A. Okay, another question down here. Right, so the question is, putting the objects together helps in terms of like memory layout, but what does that do in terms of garbage collection? Well, as I say, what it ends up doing is treating everything as a single object, so it makes the object bigger. That then depends on what type of garbage collector you're using. Once it gets into the old generation, then it's probably, it'll be treated as a single piece of data. From the point of view of like G1, it would, assuming that you have any size to it, it would have to be treated as a humongous object. So that might have some impact on how the garbage collector works. From the point of view of Zing, it doesn't really make any difference. We just treat it as like one big piece of data that's collected into the old generation. Mm-hmm. Yes, I mean, it would do. So short-lived objects, I mean, so get allocated in the young generation, and then we'll get garbage collected from the young generation, in which case it would have no impact on GC speed, because it just gets ignored. I suppose I would question whether it actually makes when there's any benefit of using structured array in that situation, because if you only have them very short-lived, then how much manipulation of that data are you going to be doing? So, but I think that's one of those things you'd have to benchmark to figure it out. No, because remember that you've got this idea of contained and container object. So the container is the structured array. So the structured array will always maintain references to the objects that are created in that structured array. So those will always be references. So you won't get any gaps because none of those objects will be garbage collected individually. The only situation where that might happen is if you remove the reference to the container and you still have one or two references to objects that were in the container. So those objects would stay in the heap. All the other objects between them would be garbage collected. But at that point, they could then be moved around because they're independent of the container, because the container no longer exists. No, you have to have both the container and the contained objects. Once the container goes away, then you can just treat the objects that were in it as if they're just normal objects. So the garbage collector can then look at those and say, are there still references? If there are, keep them. If there aren't, garbage collect. Absolutely, yes. It will work. That's the idea, is it will work completely without any changes to the JVM, without any changes to the compiler. Because in its vanilla form, it's just a new type of collection, which all of the way this works has been implemented internally in the class file. So you won't get any improvement in performance because it's not able to do anything different at the JVM level. But it's the idea that once that has been defined and can be moved into the JVM or the JDK space, then the JVM can say, okay, this is a standard library. We understand how that works. Then we can optimize it. So it can do the intrinsification at that point. Oh, yes. Yeah, yeah. But it's the way of being able to do that without breaking things as you move forward. Okay, I think I'm gonna call it time here because one more question. No, you can't do that. Because remember, you create a constructor, you create a structured array from a factory method. So you have no ability to call the constructor directly. So you call a factory method to create your structured array. That will create all of the individual objects for you. So you can tell it what you want to do in terms of the constructor, but it's the structured array that will call the constructor. So you wouldn't end up with any situation where you could have cyclic references. Yeah, because they're just Java objects. So anything you can do with the Java object, you can do with this. Yes. Well, yes, you would. Yeah, so long as the JVM understood that. So yeah, because you deserialize it, you'll just get the same object, but it would require the JVM to understand that, so it would keep it all as a contiguous block. Yeah, no, if you deserialize the structured array, then you will get the references to the object. So, and they will deserialize because it'll fill it'll. Mhm. Mm, I would have to actually have a think about that one. Okay, I'm going to call it time now because I'm definitely out of time. Thank you very much.